Alright, so this is meant to be your walkthrough for folks who either weren't here in class over the last 2 days, or if you just want to review. That's what these are usually for. I'm starting with the cover page, even though this whole thing's supposed to be about assignment 4, because I want to remind us where we've been and where we've seen a lot of this from before. And this is just something good to think about in general, is with the cover pages that I give you to these unit packets. Of course, there's the calendar that is going to give you all of the information you're going to need for every single day and every single unit. But we also have these key equations and objectives. A lot of you guys just use the equation list as your reference and then move on from there. So one of the things I wanted to point out is, as you go about studying, and this is what I mentioned in class, was that assignment 2 was all Kepler's third law. Well, mostly it was all Kepler's laws in general, but the only equation that you guys did, or we did, in assignment 2 was Kepler's third law, the ratio of the period to the ratio of the radius for those objects orbiting the same star, planet, whatever it might be, orbiting the same point. The square of the period ratio is equal to the cube of the radius ratio, and that was what we worked on for those last 5-6 problems on that worksheet. For assignment 3, this is where we got into Newton's law of universal gravitation, and that was all that we worked on really for calculating your weight on various other planets or with various other things. And we've got videos for that one and workthroughs and stuff that we've done for them. I went back and did what was it, number 3 with everyone. So if you still got questions on it, message me. But assignment 3 is where we practice that one, and even part of assignment 5, what you're going to do a little bit later on, is going to include part of that as well. What you're going to notice with assignment 4 is these two equations here. We have our velocity equation and our, make that look more like a 4, period equation. Now, if you ever forget which one is velocity and which one is period, all you've ever got to do is go down to the bottom of the page and check out this list of new variables. You'll notice down here at the bottom, I tell you exactly what each of those mean. And since this is all remote and all online now, there's no reason that you can't use this whole page as your reference when you're taking the exam. So make sure you at least know where these things are when you go to start the exam, or any of the review quizzes or things like that I have leading up to it, because this is going to be a really valuable resource for you. And I guess that's my point. Check this part out too. Common mistakes with this particular unit, right next to ways that we can be successful, right? If you're struggling, check that list of stuff out. But that was the point behind starting here, was to reference those are the two equations we're dealing with. We're not looking at any of the other ones we've done so far, or that little g equation that we haven't even mentioned yet, and that's where we're headed. So as we transition on over to the unit packet, I want to remind you guys that we have already talked about what these equations are, what each of these symbols inside these equations mean, where we got the equations from, why they're important, what they help us calculate. So while this is the first time in the unit packet we're applying this equation, my point is that this isn't the first time that we've seen it, and we should know what those pieces are. Even if it didn't mean much to you when we went through and identified those pieces, you should know what they are just by their symbols. So really there were only 2. I got rid of one of them because we dropped off a few things. We didn't include a few things because of COVID. So we have one equation for velocity. Velocity of orbiting things. It is gm over r, not r squared. Be very careful with that. Some of these equations have r squared in the denominator. Some of them have r in the denominator by itself, not being squared. And then ironically, maybe not ironically, it's not irony. I like irony. That's not irony. Weirdly enough, in this particular equation, the radius happens to get cubed. Why did that happen? Well, I derived these for you back in assignment 1, basically condensing the derivation that the book did for you in chapter 7. So I encourage you to check both of those resources out if you're curious as to where these equations came from. But this is the equation right here for velocity that we're going to use to calculate the speed of an object orbiting something else and the amount of time it takes to object that other thing. Now you'll notice in all of the stuff we've done so far, there's always been two periods, two radii, or two masses. And in this particular equation right here, you'll notice there's only one mass present, one letter M. Now, I'm not flipping a coin and deciding which mass it is I want it to be. There is no decision-making process here. We're going to talk about why this is the case in assignment 5 when we get to gravitational fields, but the reason we only use one of those masses is because the smaller mass always cancels out. In all of our proofs, all of our derivations that we did, the smaller mass canceled out, and that left only the mass of the larger object. Basically, it's the object that is being orbited. So if you're talking about the Earth and the Sun, the Earth orbits around the Sun, so we're going to use the mass of the Sun, the larger object. If we're talking about the Earth and an artificial GPS satellite that we put up there to help our, I don't know, Google Maps operate appropriately, then it's going to be the mass of the larger object. The satellite is orbiting the planet Earth, or the moon is orbiting the planet Earth, or our star is orbiting the center of the galaxy, right? Those are, whenever we're doing an equation like this, we're always going to use the mass of the larger object as the mass in our equations. We'll discuss in assignment 5 how the larger object is the one establishing the gravitational field that the smaller objects are moving through, and we'll have that conversation then. But for now, just remember from assignment 1, the larger mass always canceled out. So, number 3, if we have our International Space Station, this is where we get to the problems. Our International Space Station orbiting 400 kilometers above the Earth's surface. I'm going to draw the surface of the Earth right there. It's a beautiful Earth surface. I spent a lot of time working on it. Really proud of it. Normally, when we're talking about people on the Earth's surface, they're standing right directly on it, and there's maybe a meter between the surface of the Earth and my center of mass, or if I'm on the second floor back at Lincoln Way West. I think I'm recording this from my basement, so I'm totally not at Lincoln Way West. I'm technically under the surface of the Earth, interestingly enough. Anyways, if I'm back at Lincoln Way West, then we're probably going to be like 3, maybe 4 meters above the ground. Just depends on how tall that second floor is, right? But we're not talking about a very large distance, whereas here, with this International Space Station, I'm going to draw the solar panels off on the side. It's going to look like a really, really, really poorly drawn TIE fighter. You are welcome. If you don't get the TIE fighter reference, you're cooler than I am. Anyways, the height of this, or the altitude that this object has, is 400 kilometers. Now that 400 kilometers can be rewritten in meters. Remember, all of our stuff really needs to be written out in meters, and so that 400 becomes 400,000, because there's 1,000 meters in 1 kilometer. So it becomes 400,000 meters. Now, that is the height above the surface of the Earth. But remember, whenever we're doing any of our calculations, any of our distances, this is our 4th worksheet we've done so far. Anytime we've ever spoken about the distance between one spherical object and another object somewhere else in the universe, we always measure it from the center of that object, right? Not the closest surface to the the 2 nearest surfaces, or the 2 furthest surfaces, or one of the arbitrary combinations that you could possibly come up with. All of those different things, it's always from the center, and that's why we use the radius as our distance. The fact that I brought up the fact that my distance from the surface of the Earth right now is so small compared to, in this case, the International Space Station, is why we didn't include it so far. Here we have to include it. The total distance from the core of the planet to the crust is 6,400,000 meters. Right? That's the value that the textbook gives us. 6.4 times 10 to the 6th meters. Now, if I'm sitting on the second floor of Lincoln Way West, and I'm adding 3 meters to that, well, that's not going to change my answer very much, right? Look at how much larger 6.4 million is than 3. It's not going to influence the final answer in any way that is really going to be measurable. It will influence it, but why bother, right? Now, if our additional distance isn't 3, but is instead an additional 400,000 meters, then yeah, that's going to be a big deal. That's a significantly higher percentage of the whole value, right? That's on order of, close to I don't know, 8-9% of the entire number. I'm just doing that off the top of my head. I'm probably going to sound like an idiot when I grab a calculator, but you get the idea. It's a large enough proportion of the 6.4 million where we actually have to take into account. So when we want to talk about the total distance the satellite is from Earth, it's not from the surface of the Earth when we do this calculation. It is from the center of the Earth's gravitational field. And again, gravitational fields, I'll explain in more detail, or at least clarify what the book was talking about in Assignment 5. So that's the distance that we're going to be using for this International Space Station. If it were you and I walking around the surface of the Earth, we would just use the radius of the Earth because we're adding, what, a meter? This was adding 400,000 meters, so it was significantly more important. That being said, our equation for velocity is v is equal to the square root of a bunch of stuff. So I'm going to make it extra large. In the numerator, looking up at the top of the page, we had 6.67 times 10 to the negative 11th, because that is the value for capital G. And it's the mass of the larger thing. So which is larger? The International Space Station, which is approximately 3 football fields in area, or the planet Earth? Very clearly, the planet. So it's 5.98 times 10 to the 24th power. Again, use the e function, not because the numerator matters, but because the denominator matters. If you're not using the e function in the denominator, then you stand a very good chance of your calculator doing order of operations not an incorrect way, just the way you wrote it, as opposed to the way you intended to write it. And there's a distinction there. So let's be very careful. If you use the e function, you can't get it wrong unless you type something else in incorrectly. And that was it, right? Nothing's being squared, so I'm going to erase that dot out of habit, out of reflex. I almost went and squared that. We shouldn't. This is it. This is all. When you type in these values, you should get somewhere around 7,700, 7,800. I'm just spitballing it here. Meters per second. Right? Point is, on the exam, and this is, I want you to use the values from the textbook. Let me preface that. The textbook gives you these values for the radius and the mass of planets on page 915. I want you to use those values for these worksheets on a homework assignment, or sorry, not on a homework assignment, because you have the book with you. On a homework assignment, just use the book. It gives you all the numbers you need. On an exam, I'll give them to you. I'm not going to expect you to go hunting through a book on a timed test. So I'll give you the numbers that you need. The mass that we used here in this problem was found on assignment 3. The radius that I used here, the 6.4 million, was also found on assignment 3. So those have been provided previously. If you're looking for the information about Jupiter or Venus or whatever other planet we're dealing with in these worksheets, go to page 915. But that being said, if you don't have a book available to you and you choose to use the internet, you might get slightly different values. It just depends on how precise the author wanted to be with that particular number. You should also watch your units too. If you look up the mass of the Earth or the radius of the Earth, it might give you values that are in miles, or it might give you values that are in kilometers. You write down the number in kilometers and forget to convert it to meters, things like that. So be careful. Regardless, when we take the exam, there will only be one answer choice between 7,500 and 8,000. That's it. So it doesn't matter which one of those values you use. I'm going to try and make it very clear and distinct that, hey, this is the only one that fits that bill. Then when we go to calculate the period, how long does it take the International Space Station to do this? Remember, that equation changes dramatically. Now, radius is no longer in the denominator. It's in the numerator. So it's 6.8 times 10 to the 6th. But it's also cubed. I like to leave those parentheses there. I don't think technically you need them. I've just been using them for so long in the calculator, I honestly don't remember. But I like to wrap the 6.8 times 10 to the 6th in parentheses and then cube it. Now here's the other catch with your denominator. Be careful. It is G multiplied by M in the denominator, both of them in the denominator. So I like to do 2 sets of parentheses. You don't have to do a full-fledged bracket. I just do a bracket as another set of parentheses so you guys can see that there's 2. But I do 6.67 times 10 to the negative 11th in parentheses, multiply it by the mass of the Earth, 5.98 times 10 to the 24th, wrap that in parentheses, and then close my denominator. If you don't do this, what I've seen people send me photos of their calculators, when they send me photos of their calculator, what the calculator is doing is taking 6.8 times 10 to the 6th, cubing it, dividing by g, and then multiplying all of that quotient, whatever that worked out to be, by the mass of the Earth. You don't want to multiply at the end of all of this by the mass of the Earth. You still want to keep dividing by the mass of the Earth. So please make sure that denominator is either in parentheses altogether, or solve your denominator first and then continue the problem. Now, this last part, letter E, not going to be on the test. Same with letter B. I'm not going to ask you to add that to the Earth's radius, so don't worry about it. I'll give you the full, altitude plus radius of the planet, the distance this thing is away from the center of the gravitational field for this object is this. I'll try and make that very clear just because we haven't had a lot of time to practice this. But how many total trips is it going to make per day? If there's 24 hours in a day and it's making, well, this worked out to be, sorry, I should probably answer that for you. It was around 5,500 seconds. Again, rounding, depending on what values you used, where you got them from, should still be around 5,500. And that's going to work out to be, because I don't know how many seconds 5,500 seconds is, or how many minutes that is, I should say, or hours that is. It's like if someone tells you, oh, my child is 137 weeks old, that's ridiculous. Start measuring in years at that point. So let's convert this into hours. It works out to be about 1.5 hours. And so if you've got a 24-hour period and it makes this trip 1.5 hours per trip, then you're going to wind up with just about 16 times that this International Space Station is going to rotate, or orbit, around the center, or around the planet Earth, and that's quite a few times in one day. This sucker's moving really fast. 7,000 meters per second is tens of thousands miles an hour. It's incredibly fast. Number 4. So really, all you're going to have to let me take a step back. That was those calculations students sometimes really don't like. Just because of all of the scientific notation that's going on in there. But I want to point out, this is as complicated as those are going to get. 3C and 3D, definitely going to be on the exam, but I'm only going to ask you to solve for velocity or period. I'm not going to do something weird where I give you the orbital velocity and I ask you to solve for the planet's mass, which you could do. You just have to rearrange the equation. So I'm going to leave it very straightforward, exactly like you see it here, just because we've got less than a dozen times you're going to practice it, so we might not be as confident in our ability with the algebra as I would have normally seen you guys be. Number 4, definitely also going to be on the exam, and the reason that I'm going to leave number 4 on the exam, even though I'm only going to have one question where you calculate orbital velocity and one question where you calculate orbital period, I'm going to have several questions like number 4 that are more conceptual. So if we look at the equation for orbital velocity, remember it was the square root of gm over r, and orbital period was 2 pi square root of r cubed over gm. So if we look at these two equations and we're interested in what happens to either velocity or period if we increase our radius, not just increase it but double it, we can figure out what that is using the same sort of conceptual, we actually call this, what was it called? It just jumped out of my head. This is embarrassing because this is a recording. Factor of change problems. There it is. Found it. So it's the same sort of factor of change problem that we did with F equals ma, right? Remember back in Unit 5, if we had force equals mass times acceleration and you doubled your mass, then you knew you should get 1/2 of your acceleration. Or if you doubled your mass, then it's going to require to accelerate at the same rate twice as much force, right? We can do that same sort of thing here. I'm not going to ask you for the exact factor of change, how much it changes by. I'm just going to ask if it goes up or down. Does it increase or does it decrease? The reason I'm not going to do that is because you'll notice in one of these equations, this stuff is being square rooted, and in the other equation, it's being cubed and then square rooted, and all of that's going to get really crazy. So look at where radius is, or whatever variable I'm changing, in the equation. for velocity. Since radius is in the denominator, and I want to know how velocity changes if my denominator gets larger, it's always going to decrease. This is an example of an inversely proportional relationship. Inversely proportional meaning the larger that denominator is, the smaller the velocity is going to wind up getting. It doesn't matter what numbers you plug in there. I like to relate this back to pizza. If you've got a lot of people who came over, if you only ordered one pizza because you thought it was just going to be you, and then like 3 of your buddies drop by, now you're dividing that pizza not by 1 but by 3, and now you get less pizza, right? That's not cool. Let me know you're coming so I can order 3 pizzas. We can all eat 1 pizza each and hate ourselves later. It'll be great. But the idea is that if the denominator gets larger, velocity decreases. For period, radius is in your numerator. Oh man, I thought that was the highlighter. Radius is in your numerator, and if radius is in your numerator, not only is it getting cubed, it's getting square rooted after that, but it's in the numerator. So you've got more pizza for the number of people that are down below, because the mass of the planet and that gravitational constant, they're not going to change. So this is going to be a directly proportional relationship, and it's going to increase. Now, the reason I'm going to ask so many of these questions is because not only have we done these factor of change things before, and not only should it be something that we should be able to do, but you can also attack this from a different angle. If you don't like looking at the equations and seeing how radius might impact velocity or how radius might impact period, then go back to Kepler. Right? Go back to our conversation in assignment 2 where we talked about Kepler's observations using all of the data that he was gathered or had been gathered from Tycho Brahe and Copernicus and Galileo and all of those other people. The observations he made from that mountain of data indicated that the further away a planet is, the slower it's going to move. The slower its velocity is going to be, and the longer it's going to take to go around the planet. Or heck, even just go check out that video that we watched the very first day of this unit together in class. That is a really great visual of this exact same concept. And that's where I left everyone on assignment 4 in class. If you would like to try it, by the time we all meet again, go for it. We've got 3 more problems with those values. This isn't homework, but we've got 3 more problems with those equations using these different kinds of values. But those equations, the velocity equation, the period equation, along with the supplemental packet, the review quiz on quizzes, and the review guide, there's going to be 9 more problems using these equations. So you have plenty of opportunity to practice them for the 2 questions like it I'm going to ask on the test that will be very similar to 3C and 3D. But then you'll also get some, just by looking at your final answers, it should check out with what we talked about in number 4. That's what I'm hoping we'll be able to see, right? So Kepler made these observations. We talked about them. We found some, the video was a good source of evidence for those, but then this is the mathematical evidence for it. So however you want to square that in your head pre-tests, do whatever you got to do. Let me know how I can help.